G'day everyone, welcome to Lubrication Experts. I've got Jim here again. We're going to talk compressor oils this time around. Which is going to be really good. Compressor oils are obviously a very wide application set because we can compress just about anything. So we're not going to be able to talk, very specifically about whatever your application is. We'll have people out there who are listening who specifically want to hear about compression of some exotic gas that they have in their process, but chances are that we're not going to talk about that in detail. We'll sort of talk generically about compressors. But just to get started, if I were to look at, let's say, for example, a reciprocating compressor, very common in the industry, particularly when we need to do a high pressure compression. Just from the outside, it looks an awful lot like an engine. At a very simplistic way. It has a crankcase and it's got a piston, it moves up and down, right? But when you look at an engine oil versus a compressor oil, they look like entirely different species, right? So engine oils tend to be what you would call, like, among the lubricants, seem to be like quite highly additized.
Yes.
Got to get additive chemistries, even just like on a volume basis, additives make up quite a decent proportion of an engine oil. Versus you go over to compressor oil, which seem to be, let's say, in the ballpark of basically 99% base oil with a small amount of additization. If I could speak very generically about engine oils and compressor oils. So if an engine looks like a compressor, but an engine oil looks nothing like a compressor oil, that might be a good starting point to describe the differences and what makes a compressor oil a compressor oil.
Yeah. So compressors are a perfect springboard to think about the discussion about how the mechanical device drives the chemistry, right? So when you're dealing with engine oils, you're dealing with lubricating a crankshaft with hydrodynamic bearings. You've got connecting rods that are going around like a bicycle pump, crank. You've got the lubrication and sealing that the rings around the piston have to do, as well as a whole rafter of other coordination events, the movement of the valves, the intake valves and exhaust valves, and back and forth. But in an engine, you've got to deal with not just lubricating a hydrodynamic machine that's got to spin ad infinitum, but you're dealing with combustion gases. The bugaboo about even an extremely efficient engine today, the most efficient engine, the combustion process, is maybe 98% efficient in terms of converting the liquid hydrocarbon into carbon dioxide during an explosive event initiated by the spark plug, right? So you deal with a huge expansion of gas and energy, and that's how you propel the piston up and down to extract work on the flywheel to make whatever you want to propel forward or do work. So that explosion that happens with a typical engine oil introduces millions of different species on a microsecond basis. Every time there's a power stroke, into the lubricant that's on the cylinder wall and down into the crankcase by gases blowing by the rings. Not much happens that way, but most of it is diffusion into the thin film on the cylinder walls. So you've got free radicals, you've got acids, you've got sulfur species, you've got a little bit of phosphorus, you've got whatever's in the fuel, whatever's in the ambient air is being partially burned, oxides of nitrogen, right? So the air itself is burning, and a little bit of that is getting into the engine oil. You say, well, that only happens, there might only be like 4 parts per million with every explosion event. But, think about the typical four-cylinder engine that's in your car, sitting there idling at 1,000 RPM. that means every minute in every cylinder, there's 500 of these diffusion events going on at idle. And then you rev it up and you start demanding more and more power for more and more fuel. You can see that engine oils easily get overwhelmed. And that's why they need to be changed out with relative high frequency. The additives get saturated with all these combustion byproducts, right? In a compressor, you don't have that, right? So something else is driving that piston up and down, right? So you've got the reverse happening. Instead of the piston driving the flywheel, something, an electric motor, another engine, a hydro wheel, whatever, a little guy turning the crank, right? It could be that simple, right? So is driving the piston backwards relative to the automotive application, right? So in the automotive sense, the chemistry is driving the piston, drives out the flywheel, and in a compressor, it's the other way around. Some other machine is doing work on that piston. So as such, number one, you don't have the combustion byproducts to worry about in a compressor, right? That you do in a reciprocating engine. And number two, you really don't have the super high temperature events. You do have some high temperature events you have to mitigate in a reciprocating compressor on the reed valves if it has a typical two-stroke design. But you don't really have these crazy high thermal events that you have to manage all the time. The lubricant itself does a better job at mitigating the temperature effects inside the reciprocating machine in the compressor. So the base oil is doing most of the work in that sense, relative to an engine oil, which is the other way around. The additives are being held there by the base oil to intercept all this combustion byproduct nonsense that you have to deal with. So a lot of it is just looking at the machine and what it's actually doing. So the machine work of compressing gaseous fluids, if you will, is another machine doing work into the compressor. And in an engine oil, the engine is converting chemical energy into mechanical work, going backwards. And that's really sort of the essence of the difference, and why you don't need these heavy additive loads in a compressor oil relative to an engine oil. The lack of contamination.
Yeah, that makes a lot of sense. So then, and these two questions might kind of go together because obviously we compress many different gases. By volume, it probably goes air compression and then like natural gas compression, and then there's the whole host of refrigerants, and then you've got all your exotic, process gases. So we need to, be able to select compressor oils for all these different applications, even though the machinery might be the same, but the actual gas that we're compressing might be different. So could we talk a little bit about how does the gas that you're compressing affect the formulation? Because if I think off the top of my head, through the product ranges I've seen, I can pretty easily name mineral compressor oils, polyalkaline compressor oils, ester-based, diesters, polyalkaline glycol compressor oils, and they're all sort of geared towards a slightly different application, right? Like you might use a PAG for gas compression. I've seen synthetic PAOs used for air compressors. So how does the gas that we're compressing affect maybe the lubricant?
Oh, tremendously. If you want to just limit the overview right now with reciprocating compressors, as opposed to bringing in rotary screw compressors.
For the moment, yeah.
Okay, because I mean, there's a whole evolutionary change that I've witnessed during my 30 years of working career. But if you talk about reciprocating compressors, we'll just leave it there for the moment, instead of going to rotary screws. So something just danced on the machine, on the screen here. You're much larger. So So if you think about just compressing air, which is what I would say, I don't know, you're more of a field guy than I am. 85–90% of all compressors are used to compress air for a variety of applications. I'm just guessing. Oh, I don't have a voice for you, Rafe.
So I was going to say that that's probably in the right ballpark.
Oh, okay. Yeah. So when you're dealing with air compression, by and large, you don't worry about ester versus PAO versus mineral oils, except for an alkylated naphthalene and PAGs, except for the durability of the lubricant, right? So this goes back to the general sort of rule of thumb. If the lifespan of a mineral oil is 1x, let's say it's a year, from a PAO doing the same kind of duty in that same machine, you can get 3 to 4 years. And alkylated naphthalene, you can get 7 to 8 years out of the same single lube charge, right? So that there gives you the sort of durability of the different hydrocarbons. Esters, you can sort of put esters at about on par with pure PAOs, maybe a little bit less. I would put them, say, 70% less, certainly better than mineral oils. And polyalkaline glycols, that's the other wild card. PAGs are interesting, is that they, depends on the application, you can actually get durability that's anywhere from 2 to 3 times that of a synthetic hydrocarbon, which would be sort of 10 times better than a mineral oil, but not as good as alkylated naphthalene. So that's where I would sort of slot PAGs in there, just for air compression. Now, when you get into changing the gas, like we'll talk about natural gas or methane, right? So here there's a big controversy going on about calling it natural gas in North America, right?
Right.
It's really mostly methane, right? Because of fracking and all this other nonsense that's going on here. So if you think about methane will dissolve into a hydrocarbon. I've actually worked several issues during my career. I've watched ISO 460 gear oils being used in a compressor. 1% methane will dissolve in that ISO 460 oil and turn it into an ISO 46. It's astounding. The viscosity drop is amazing. And that methane will stay dissolved at an equilibrium concentration at relatively high temperatures in that high viscosity lubricant for a protracted period of time. Depends on how much gas is being blown in and the pressure and all those other variables. But that's why when you go out on drilling platforms, you tend to see these big aerial reciprocating compressors for methane compression. They tend to be lubricated with PAGs, polyalkaline glycols, because methane doesn't dissolve in polyalkaline glycols. You can select the viscosity you want. The PAG will dissolve. It'll attempt to dissolve in that bulk fluid, but it'll just stay as an isolated bubble and eventually percolate out of the solution. Whereas if you had a hydrocarbon, the methane would eventually diffuse and dissolve into the hydrocarbon. So with methane, hydrocarbon processing in a refinery, you probably want to stay away from hydrocarbons because you will do a lot of damage. And I've seen a lot of very happy customers with polyalkaline glycols. They're unhappy about the cost and the difference in maintenance because you can't mix them with anything else. But for viscosity applications, they're incredibly stable. And then all bets are off when you get into other applications. You get into reactive species, now all of a sudden you can't use esters. You can't use PAGs because a polyalkaline glycol will hydrolyze with a strong base and highly reactive chemicals. And depending on how reactive the gas is, if it's chlorine gas, you can't use a mineral oil because the residual olefin content and the aromatic species will react with it. So you've really got to you really got to have there's got to be a little bit of chemistry knowledge that has to go with the choice of lubricant based on the process and the machine.
So maybe just to
it,
expand
it,
there, yeah, so I can kind of help contextualize that chemistry discussion. So let's say, for example, let's pick up on one of the reactive species. You talked about compression of chlorine gas, and you said that if you have olefins, that that can pose a problem. So my understanding of the way that chlorine works, and this is just from my time as actually as a competitive swimmer, swimming in chlorinated pools, is that the whole point of putting chlorine into the pool system is that by and large, it's able to break the second of a double bond. And that's why it's used basically to kill bugs, is because it goes after the organic compounds in bacteria and viruses and stuff. Now, I have no idea, because that's research that I probably did in about year 7, but it seemed to pass muster. So, is the idea that if you have a mineral oil compressing using a compression application that's compressing a chlorine gas, that any chlorine gas that comes into contact with a mineral base oil, which is going to contain some unsaturated hydrocarbons, right? So that means there will be some double bonds in the base oil, that the chlorine will be reactive enough that it's going to then break those bonds and effectively oxidize the base oil. Is that what you were getting at?
Yeah, if there's any residual olefins in there, that's exactly what's going to happen. You don't have any of that when you're dealing with synthetic PAOs, for example, or alkylated naphthalenes. Eventually, the alkylated naphthalene will react with chlorine. It'll do the aromatic substitution reaction. But the olefins, any kind of olefin there's probably not going to be any olefins, because most of these base stocks are hydrotreated in the refinery, right? So there's not going to be that much residual olefin. But in service, mineral oils do generate olefins as a decomposition product. So what tends to happen then, if you chlorinate a double bond on a hydrocarbon, you're just asking for it to do a coupling reaction. And then once you start coupling reactions, then molecular weight and the viscosity starts to skyrocket. That's sort of the normal suspects that operate in decomposing things with highly reactive gases like chlorine.
Yeah. And then the other one that I wanted to pick up a little bit on as well was that you talked about the effect of bases on polyalkaline glycols. So what's the reaction that's happening there?
So there you're dealing with the retropolymerization reaction. So if you think about a polyalkaline glycol in the simplest case, it's oxygen, carbon, carbon, oxygen, repeat. Oxygen, carbon, carbon, oxygen. Oxygen, carbon, carbon, oxygen. So if you think about how that polymer was built, it was built from a series of oxiranes or epoxides. So that was 2 carbons and an oxygen in a 3-membered ring. And then a base comes along and opens it up. And then this oxygen then reacts with another, and then it forms a polymer of however many monomers you want to make it. That's the beauty of polyalkaline glycols. You can tune the viscosity based on the reaction residence. But eventually what happens is that you've got to decide with that PAG, in the manufacturing process, you generally start it with, say, butanol, C4 oxygen, oxide, and then you have a terminal oxygen that you need to cap in some form. So that's stable, it's fat, dumb, and happy, doing what you want it to do. And then all of a sudden, some reactive species comes along and rips off that terminus piece that you've capped that last oxygen with, and then the whole process reverses itself. And poof, you generate a tremendous amount of very low molecular weight oxiranes or epoxides. So essentially the polymer falls apart into its sort of natural gaseous, not natural gaseous, but its beginning gaseous form. And that's one of the big downsides of PAGs, is that with highly reactive basic species, they do synthetically depolymerize, and then that causes all kinds of problems with the residual materials.
Yeah, that's interesting. So I mean, in a very basic term, it kind of like almost unzips or unravels.
Unzip polymer. Yeah. Actually, there's a very famous, for 40 years now, Chevron has sold this fuel additive called technolon, and it takes advantage of that retropolymerization reaction by diffusing into heavily laden carbon deposits inside of an engine. And then at a certain temperature, there's a light-off temperature, and it depolymerizes, and it generates a tremendous amount of ethylene oxide gas. And it mechanically ablates deposits on heavily abused older vehicles. And it's rather unique. Their patents are long expired, but Chevron Chemical has, all the processes, and they know how to. They have that, magic molecular weight, the magic tail, the magic terminus, and they know exactly how the technolon actually works. So if you have any motor vehicle that's got a problem, use the Chevron technolon product, and you'll remove all the intake manifold, the combustion chamber, piston crown, cylinder head. You don't have to take the engine apart. You just run a tank full of this stuff in there, and it's actually quite amazing how effective it is in terms of cleaning up the inside of your engine. So that mechanism has been well known and has been exploited by many chemical manufacturers, Chevron in particular. So
yeah, that's really interesting.
Something you have to. Go ahead. No. What's really interesting is that is it's the two-edged sword of being a chemist, right? You get to choose. Do I use this reaction to my advantage if I'm Chevron, or do I have to worry about this if I'm a polyalkaline glycol lubricant user?
Yeah, and this is one of the things that I guess I'm trying to promote a little bit with this with these interviews is most end users of a lot of these lubricants have a mechanical background, right? We're often mechanical engineers, or we're fitters or mechanics or whatever, without and I include myself in that bucket, without a very firm understanding of the lubricant chemistry. And unfortunately, lubricants are chemistry, and it's a sort of an essential component of understanding how they work. And so, like you said, with compression applications, it would be very easy. Let's say, for example, if we're getting caught short on stock, and you have a 460 weight polyalkaline glycol, and you think, I'll just use that, because you don't understand necessarily why that's a terrible idea in some specific application. So it's really nice to kind of dig down into a little bit of this chemistry as well. And that certainly
sure. That's one of the things I applaud your efforts with this, because it's really irritating to me, as someone who's gone to STLE meetings and WEA meetings and wind energy. I mean, I would go to a lot of these wind energy association meetings in the US or even in Europe, and there'd be a few hundred people in the room, and I'd be the only chemist. And the first day, it's back and forth. I give my presentation. They're like, "Oh wow, here's a chemist. Let's see what this guy thinks about all this other stuff." And I'm like, oh. And it's one of those things where, it's not it's nothing magic. It's nothing mystic. It's just that if you don't understand it, it appears to be magic, right? And all it really is just understanding the language of the periodic table. I mean, that's how my education, ever since I was in high school, before I went to my first degree university and decided to be a chemist, I just was fascinated with how the world is put together. And to me, it's just, it makes perfect sense how things go together and taken apart, and how things interact with each other. But, as someone who has spent a lot of time inside my own head dealing with the chemistry piece and interpreting things, it's gratifying to me when I can get someone to understand the basics of the science and not be incorrect. One of the fears that chemists have is to be misinterpreted as things are being too simplified. But things are quite simple. It's just that it's one or two more steps, not 50 steps. You know what I mean? You don't have to be a wizard. You just have to be, insightful enough to be able to come up with the correct sort of grounding in a metaphor or explanation of how things work for the listener, right? It's all about the listener. I spent a lot of time helping my two sons who are Boy Scouts here, the Boy Scouts of America, and we have a saying in the adult leaders is that you really need to be able to explain everything to a sixth grader. So if someone who's 11 or 12 years old can't understand what you do, why you're doing it, you're essentially wasting your time, right?
Yeah.
You have to really, not that mechanical engineers are sixth graders, I don't want to say that, but I mean, it's just that seems to be the point at which everybody sort of starts to bifurcate and move off into their own little branch of inquiry and knowledge, and I don't think the chemistry is all that mystical. It just needs a little bit more of a calm explanation, because the downside of choosing something wrong is usually financially and could be, a tremendous safety problem, and that's the biggest problem with chemistry, is that you can really screw things up in a hurry if you're not just sort of thinking through the problem a little bit.
Yeah.
So I applaud your efforts to try and demystify this. This is really a great thing you're doing. It's really great.
We briefly touched on let's say the nuances of screw compressors versus reciprocating compressors. Now, I know that we're opening up a whole can of worms, or Pandora's box, or whatever, but maybe if we can talk generally, there are obviously a whole bunch of different compressor types, right? Not just rotary screw compressors, but centrifugal compressors as well. So how do the different compressor types also change the lubricant as well?
Oh, that's a great question. From my perspective, during my career, I would say somewhere around the late 1990s, right, before Y2K, you could look at the market for reciprocating compressors, at least here in the U.S., and that's all my perspective is, right? Maybe 80% of most compressors for light industrial or even commercial applications were reciprocating compressors, and a minority, say 15%, were screw compressors. And in just a very short period of time, with computer-aided machining and all this technology for computer-controlled welding and everything else, I saw that reverse, so that the reciprocating compressors went from dominating the market to being a small minority in the medium to light industrial applications. And the screw compressors essentially take over 75–80% of the volume demand of machines and therefore lubricants by the time I retired a few years ago. So it's really been quite amazing to watch that transformation happen. And screw compressors are, they have a lot less moving parts. There's in theory, there's no contact with the rotors against the stators. If that happens, essentially the machine's gone. You've got two sets of carrier bearings on the two scrolls, two fluted castings that interact with each other. And you have a spring-loaded valve that controls the pressure that goes off into the pressure vessel. A very simple device compared to a reciprocating compressor. So I could see why people who, let's say contractors, they would rather plunk down the $10,000–12,000 for a portable screw compressor, instead of say $7,000 or $8,000 for a reciprocating compressor that has all the maintenance associated with a reciprocating machine, right? You've got less frictional moments to deal with, and screw compressors they can go typically 60, 70, 80,000 hours of operations between rebuild cycles, right? That's screw compressors. Reciprocating compressors, you're going to be lucky to get 10,000 hours between rebuild cycles, right? So there's a lot of inherent advantages to choosing a screw over a recip. And I perceive the way the industry and operational community has gone that way. And if you look at the lubricant demands, you had touched on one of your previous episodes about how lightly additized reciprocating compressor oils are, and believe it or not, they tend to be fairly simple additization methods for screw compressor oils. But screw compressors, oddly enough, because the operating temperatures of the bulk sump and the machine parts tend to be a lot lower, the drain intervals for screw compressors are much lower. You don't have these crazy spikes in temperature of, say, 170, 180 C that you'll see sometimes on the parts of a two-stroke reciprocating compressor. Over on the screw side, on a really bad day, it'll be 130 C, right? So you tend to see a lot different, more mild conditions on the screw side as opposed to the recip side. The lubricant can be optimized for very, very long drain intervals. For example, alkylated naphthalene dominant lubes in screw compressors really shine. The SAC Rare, the mobile SAC Rare series is a great example. You can get, 3.5 year drain intervals out of a screw compressor oil. Over here on the recip side, you have to change it out every 10, 12 months.
When you say that you're optimizing, you can do a lot more optimization on the screw compressor side. Is that because the lubricating, let's say, regimes that are required are not quite the same? So on the recip side, we talked about it being quite similar to an engine. So you've got,
yes,
your crankshaft bearings, which are, have to be, there's a certain lubrication requirement for those. The pistons have a slightly different lubrication requirement. So is that, whereas for the screw compressor, it's more or less the bearings, right?
Yep.
Is that the
Bearings
reason you get more optimization?
Yes. You're really talking about a bearing oil that has to be adapted for compression, and so that you can drop the viscosity. Roller element bearings, whether they're spherical, ball bearings, or cylindrical roller bearings, they love ISO 100, ISO 150 all day long. That's what they want. Doesn't matter what the loads or speeds are. They're pretty much in a fairly narrow band there. Most screw compressors I've seen taken apart, they're all tapered cylindrical bearings. But the best lubricant because in a compressor, the lubricant's not just cooling and lubricating bearings, it's acting as the seal around the two rotor pieces and the stator. So that viscosity generally is right around ISO 46, ISO 68. That's sort of the magic viscosity that you want for screw compressors. And that's, most bearings are, the bearings that are in the carrier bearings for a screw compressor are very lightly loaded. They're not, big bearings, heavily loaded bearings you'd see in a wind turbine, for example. Although anatomically they look similar, their duty cycle is a lot lower. You could get away with an FCG 8, for example, in compressor oil. Yeah. But the key thing with the compressor oil is forming that film, that tiny little film of lubricant, because if you look at the way a screw works, it's a continuous induction of gas bubble or air bubble that comes in the front side of it. And as the air bubble moves through the flutes of the screw, it compresses 10-to-1, 12-to-1 as it's moving through the tops of the screw flutes to the high pressure storage vessel on the back side. And they're very simple devices, but so at the end of the day, all you really have to worry about in a flooded screw compressor application is making sure you maintain that film between the clearance between the rotors and the stators, and whether or not the bearings are happy, so you can't go crazy with the viscosity one way or the other. So I personally think, for unless you have very specialized applications for reciprocating compressors, you're going to see in the next, high pressure, trained, one cylinder leads into another for compressing things to higher pressure. I honestly don't think you're going to see a lot of reciprocating compressors, re-entering the market. You're going to see more optimization of screw compressors. That's what I think.
Yeah. And that sort of leads into the last question I really wanted to ask, which was around the future of compressor oils. I personally, my career has been reasonably short, but I haven't seen that much change in the compressor oil market, let's say. So like you said, in the 1990s, we had a big shift in the light to medium industrials from reciprocating to screw compressors. That trend seems to be pretty baked in now. And likewise, the lubricants that have been formulated for use in all these compressors don't seem to have changed significantly over the last few years. And not only that, but the selection that we have does seem to last for quite a long time in most applications. You can get some pretty long drain intervals, and they seem to do the job really well. So the question there is, like, have we reached peak compressor oil, so to speak? Do you see that there are going to be any significant developments, or what we have is, it seems to do the job at the moment? So do you see that market being relatively stagnant for a while?
Yes. Okay. So I do see the market sort of stable, and for the foreseeable future. That would be, 5, 10, 12 years out. I don't think the relative dominance of the 3 compressor types, recips, screws, and centrifugals. The centrifugals are pretty much, they're very specialized, I think, for their applications. Very high volume, medium pressure, right? Screws are more portable and easily brought to bear in terms of consistent. The nice thing that screw compressors bring, as I understand it, from just my simple renting of a jackhammer for demolition purposes a couple times, is that reciprocating compressors give you pulsed air, and you have to deal with that change in the number of cylinders and the high pressure exhaust side of things operating your tool. Whereas if you have a rotary screw compressor, you have nice smooth air. It's a nice, that the high pressure reservoir is nice and controlled. You don't have large pulsations and changes in pressures and volumes. And that's really sort of the elegance of a screw compressor. But I don't see a fourth design out there. Where is it? Peristaltic, little diaphragm things. They're just little tinker toys that you use in labs here and there. But for big industrial applications, there's going to continue to be centrifugal applications, and they're going to be limited. And by and large, you're just dealing with the yin and the yang of compressors, or recips versus screw compressors. Yeah. So I don't see a big explosion. I don't see a machine out there that is going to lend itself to a new mechanical revolution in compressed air.
Yeah, and I guess then as lubricants as a following technology means that if there's no significant technology changes on the equipment side, then we're probably not going to see any on the lubricant side either.
Yeah, sure. And then at the end of the day, when a new machine comes out, what's the first lube that people? There's 2 lubes that people reach for, right? You come up with a new machine. First lube is an engine oil. Let's find a synthetic. Go to the carport store and see if it works. And huzzah, it doesn't work. Or they go and they reach for something like Mobil SHC 600, right? The classic Swiss Army knife.
Yeah.
So just, hey, let's see if the Swiss Army knife works. And maybe 85% of the time, either of those 2 lubes work. And then you go down the rabbit hole of needing a specialized lube for a very specific machine. And I've witnessed that several times in my career. That the usual suspects. It's kind of like Casablanca, and Humphrey Bogart. Round up their usual suspects. The usual suspects are engine oils and SHC 600. And if they don't, those two criminals don't work, then you have to pull out the big guns and start thinking about something specialized. So yeah, I don't see a big revolution happening, but I'm just a dumb old chemist from Jersey, so I'll put that out there as a proviso.
Sounds good. Hey, well, Jim, really appreciate your insight. I think people will get a lot out of the compression discussion. So, yeah, really appreciate your time, and we'll talk again for the next round.